In our last lecture, we discussed the concept of free body diagrams and the conditions of equilibrium while analyzing the equilibrium of a system of rigid bodies. In today's lecture, we will make use of these concepts in a very important area called structural mechanics. So, today's lecture is titled Structural Mechanics. What is structural mechanics? This branch of mechanics involves the analysis of equilibrium of structures using, as I said, the concepts of free body and equations of equilibrium. We will be studying two types of structures, namely number 1 trusses, number 2 beams. First we will start with the analysis of trusses. What is a truss? Truss is an assembly of members or elements that are fastened together to support stationary or moving loads. They may be fastened through riveted joints, welded joints or pin joints. I will give you some examples of trusses. First of all, two-dimensional trusses or plane trusses. Here is such an example. The member, these are the green lines are representing the members or elements of a truss, and the whole assembly is a plane or two-dimensional truss. You must have seen such structures or such trusses while crossing a railway bridge. On the both sides of the train you can see a series of such structures which support the load of train as well as other members of the structure. The other example of plane truss is when you visit a workshop or a go down and you look up, you will find that the roof and other loads are supported by through a series of plane members, plane structures, and they are also examples of trusses. The three-dimensional truss or space truss is a similar structure, but it is in all the three dimensions, that is length, breadth and height, and the example of such truss is you will find in power transmission towers for the distribution of electricity, etc. Now, the basic element in the plane truss is a triangle. You can see that each one of them is connected to the others like this, whereas for a three-dimensional or space truss, the basic element is a tetrahedron. We will be mostly concentrating on the analysis of two-dimensional or plane trusses, and before we take up the analysis of these structures, let us make some simplifications or idealizations. Number 1, each member of a truss is loaded at the two ends of the member, that is, we are neglecting the self weight of the truss or any other transverse load which may be acting on the members. You may recall that when there are forces only at the ends of a member, it is a two force member, and from equilibrium consideration the force has to be collinear, passing through the two ends or two pins of the member. So, in that sense, the forces in the members of the truss will be either tensile forces or compressive forces. Number 2, the forces at the joints are concurrent, that is, joints where various members come together, these are called joints. For example, going back to the picture, this is one joint, another joint, etc. So you can see that over here 1, 2, 3, 4, 4 members are coming together. They are meeting at a point, and although we are representing these members as lines, that is they are represented by their axes. So all these 4 axes, they meet at a point, and since the forces are along the axis of each of the members, it means that the forces on the truss members are concurrent forces. And third condition is truss is statically determinate, that is we will consider only those trusses which can be solved with the help of equations of equilibrium. No other concepts or no other equations are needed, although in more complex civil engineering structures sometimes we make use of statically indeterminate trusses, but we will not be considering them. Fourth idealization or simplification is that the truss is just rigid. Well, what is just rigid truss? There are 2 types of trusses, just rigid and second type is over rigid. In the case of over rigid truss, if we remove one member, the truss does not collapse. It can still maintain its shape and take up loads. But in the case of just rigid truss, if you remove one member, the whole structure can collapse as soon as you apply the load. For example, again going back to the example of the truss which I have shown for the 2-dimensional case, suppose there is an additional member here. Well, without this member also the truss was maintaining its integrity, that is it does not collapse. So it means that by putting an additional member here or member here, we are making the truss as over rigid. Now what are the conditions to ensure that our truss is just rigid? For a 2-dimensional case, the following condition should be checked. M is equal to 2j minus 3, where M is the number of truss members, J is the number of joints. For a 3-dimensional truss, M is equal to 3j minus 6. Let us go back to our example. Here is a 2-dimensional or a plane truss. Now let us count the number of joints. 1, 2, 3, 4, 5, 6, 7. So 7 joints, it means number of members should be 2j minus 3, 14 minus 3, 11. So if you count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it is just rigid. Similarly, you can make a simple calculation for a 3-dimensional truss. One thing more, when you look at the plane truss, the basic element of the truss is a triangle. Now if I start with this triangle, I add 2 members here and 1 joint. So I get a truss of this type. If I add 2 further members and 1 joint here, so you get, so in this way, by adding 2 members and correspondingly 1 joint, you can build up the whole truss. So those trusses which are built up from simple triangles in this manner, they are called simple trusses. So now after having understood what are the requirements for a just rigid simple truss and restricting ourselves to the plane case, we will now look at how to analyze for the forces in a truss. So we start with the procedure for analysis of a truss under applied loads. Okay. Mind you, the loads are only to be applied through the joints. No in between forces can be considered here. First of all, you check that the truss is statically determinate. okay, that is the number of unknowns from the that is unknown forces as produced by the supporting conditions, they should be equal to the number of equations available for the equilibrium. For a plane case, you remember we have 3 conditions of equilibrium. It means if there are 3 unknown reactions from the supporting structures, foundations, etc., or supporting pillar, then the truss is statically determinate. After having ensured that it is statically determinate, then we go ahead and obtain the 3 reactions for the case of plane truss and 6 reactions for the case of space truss or 3-dimensional truss. And after getting the reactions from the supports and conditions, then we solve for the forces in each and every member or as required in given number of members of the truss. There are 2 methods available for determining the forces in various members or elements of truss. Number 1, method of joints, and the second is method of sections. So, we will start with method of joints. Well, in the method of joints, the solution proceeds from one joint to the other. At every joint, since the forces are concurrent forces, therefore, only 2 equations of equilibrium are available. So, it means I can solve for only 2 unknown forces. What are those 2 equations of equilibrium? Sigma Fx is equal to 0, that is sum of all the horizontal forces acting at that joint is equal to 0. Similarly, sum of all the vertical forces at that point should be equal to 0. Now, how to label these forces, how to identify whether these forces are tensile forces in the member or compressing forces on the member. Generally, we identify the forces as to how they are acting on the joints. For example, suppose there is a joint over here and a joint over here. So, if the force is such that it is pulling the joint like this or this joint in this direction, then by equal and opposite reaction, it means the member is pushing the force in the member will be like in this direction. That is, these are the forces as they act on the joints, and in the case of compressive forces, it means they are pushing the joints like this. Okay. So, the tensile force in the member is identified by the arrows inward along the member, and similarly the compressive forces are identified by arrows outward along the members. So, please remember that is the arrows are according to the direction in which the forces are acting on the joints. Let us see one example and then solve it with the help of method of joints. Here is a simple truss. You can easily see that it is just rigid, that is by counting the number of joints and the number of members, you will see that the condition that m is equal to 2j minus 3 will be satisfied, and it is built up from simple triangles. So, it is a simple just rigid truss. And also, suppose if I had put an additional member along BE, then it will become an over rigid truss, but fortunately that member is not there. we are having a just rigid truss. Now, here is two supports on the truss, A and D. D is a roller support, A is a simple or pin jointed support. So, you can see that there are three unknown forces from the supports, that is two reactions at point A, one in horizontal direction and one in the vertical direction, and one reaction at D, that is only vertical reaction. It cannot sustain any horizontal reaction because of the rollers, it will start translating. So, there are two at A and one at D. So, three reactions, and the conditions of equilibrium available in a plane for such a truss are also three. So, the truss is soluble, hence we can say that it is statically determinate. Now, first of all, we will consider the entire truss as a free body, that is, we will isolate it from its supports by putting two reactions. Now, in all these problems, first you should identify your coordinate axis. Let us say horizontal is our x axis and the vertical direction is our y axis. Okay. So, at A there will be two reactions, Ax in this direction and Ay in the vertical direction, and at D there will be a reaction dy. Okay. So, these are the three reactions. So, let us consider the truss as a free body, the whole truss as a free body, three conditions of equilibrium, sigma fx is equal to 0, sigma fy is equal to 0 and sigma mz about any point A. Now, why we have chosen point A? Because at point A there are two unknown reactions. Okay. So, both Ax and Ay will have 0 moment about point A because they pass through point A. So, our conditions will be very our equations will be very easily solved. First of all, Ax is equal to 0. So, in the horizontal direction there is only one force Ax and no other horizontal force. So, immediately we know that Ax is equal to 0. In the vertical direction, what are the forces? There is a 5 kilonewton and 2.5 kilonewton downward, both of them, and there are two vertically upward forces Ay and dy. So, you can easily see that here is Ay and plus dy minus 7.5, two downward forces equal to 0, and then you take the moments about point A. So, this whole length is 3 plus 3 6 9. So, this will be dy into 9, and that is in the anti-clockwise. So, it is positive, and this will be 2.5 into momentum is 6, that will be clockwise. So, minus 6 into 2.5 minus 3 into 5. So, you can say 9 dy minus 6 into 2.5 minus 3 into 5 equal to 0. So, these three equations immediately give us dy, that is the vertical reaction at D is equal to 3.33 kilonewtons and Ay is equal to 4.167 kilonewtons and Ax is 0. So, we have solved for the three unknown reactions. Next, we start with joints. Okay, we will start with one. Always start with a joint where there are only two unknown forces, because only two equations are available. So, if I look at the truss once again, joint A has two members. So, it means there are two unknown forces. Now, start with joint A, draw a free body diagram of all the forces at A, and then for the time being you assume the forces in, let us say, member AB or AF either away from the joint or towards the joint. We can't presuppose that it has to be tension or compression. We arbitrarily make a choice. So, what we have done here is, I have taken the force along AF towards the joint and force along AB also towards the joint, and AX is equal to 0 and this is AY over here. So, this is, we have found out AY as 4.167 kilonewton. So, sigma Fx is equal to 0, sigma Fy is equal to 0. Well, sigma Fx is equal to 0 means minus, because positive x direction is towards the right, this force is towards left. So, minus TAB minus the component of TAF along horizontal. So, minus TAF into cosine theta is equal to 0. Similarly, we can write for Fy. There is a vertically upward force of 4.167 and this will have a vertically upward component of TAF sin theta. Now, from the geometry of the truss, you can find out what is angle theta over here. This is angle theta. So, this is 3 meters, 4 meters. So, sin theta and cosine, and you can easily see that by Pythagoras theorem the side AF will be 5 meters. So, sin theta will be equal to 4 by 5, cosine theta will be 3 by 5. So, 4 by 5 sin theta is equal to 0.8, cosine theta is equal to 0.6. You substitute sin theta and cosine theta and solve for from equation 4 and 5 for TAF, and this will be negative sign here, TAF and TAB. Now, this negative sign in the evaluation of TAF means that the actual direction of force in the member TAF is opposite to the assumed direction. See, we had assumed the TAF to be towards the joint, okay? That is, it is pushing the joint, compressive force, but because of the solution which shows that it is negative 5.21, it means actually the force is away from the joint, okay. So, it is a tensile force. So, TF is 5.21 kilonewton tension, TAB is equal to 8.68 compression, okay. Now, which joint we should proceed next? Joint B. In joint B, there are 3 members. Now, this joint is very simple to actually solve for. There is no vertical force, so it means TBF has to be equal to 0. If we consider sum of all the vertical forces is equal to 0, no applied vertical force here. So, it means the member BF does not require any force. So, TBF, and in the horizontal direction TAB is already known, and it means TBC will be equivalent opposite to AB. Force in TBC in BC will be equal to that in AB. So, it will be 8.68 kilonewton. So, again it will be a compressive force. TBC will towards the joint. So, it means it is a compressive force. Now, next we will take the joint F. If I again show you this joint F, okay. So, after this is how we proceeded, A to B, B to F. Now, in this case we have, it appears that there are 5 forces, 1, 2, 3, 4, 5. This force we have already found to be 0. This is a given force. This force TAF has been already found. So, the unknown forces are only force in the FC member and force in the FE member. So, again there are 2 unknowns, and hence two equations of equilibrium will be sufficient. This is joint F. Okay. So, sum of horizontal forces, again you can now, by now you are very well versed with this, and sum of the vertical forces is equal to 0. You write down the equations, substitute for sin thetas and cosine thetas, you will find two equations, and solving for two unknowns you will find that TFC is minus 1.04. Now, minus implies that our choice of arrow was wrong. It's actually the arrow should have been opposite. So, it means it's a, we had chosen it as a compressive force, but actually it is a tensile force. TFC is positive, it means our choice of arrow was correct. So, it is a tensile force. So, from joint F, now we proceed to joint E. Again, joint E is very easy to evaluate. Once again, if I go back to joint E, see there are two members here, one member over here, and this member TFE has been already found out. So, only two unknowns. Out of these two unknowns, this force will be exactly equal to the force in this CE member, and this force will be exactly equal to the force in the FE member. Okay. So, at joint E, simply by inspection we can write down TEC is 2.5 kilonewton tension, TED is TF equal to TFE 2.5 kilonewtons in tension. And finally, we come to the joint D, which is the supporting joint. Well, just one unknown force is needed to be calculated, TDC, that is we will have one equation, sigma of Fy, sum of the vertical forces is equal to 0, which will give us TDC is equal to 4.167 kilonewtons. Okay. Now, if I go back to this joint, this is the joint, we have already found out dy. Now, as a check, do we get this condition that the component of the force in TDC is equal to the applied reaction and the calculated reaction dy? If the check is okay, it means our whole analysis was okay, no error was committed. So, let us see. Is TDC cosine theta, that is the vertical component of TDC, which we have found out to be 4.167, is it equal to the this is the horizontal component, is equal to the TED, which we have already found out here, and it is indeed so. So, it is 2.5 kilonewtons. So, it means our analysis was perfectly okay. So, this was the method of joints. Next, we will well, before I close up this analysis, I have drawn the truss once again with all the force members. Okay. These are this is the complete solution of the truss problem, and here are the reactions, and these are, you can see that these are compressive, tension, etc. So, you can immediately recognize which member is in tension, which member is in compression. So, this completes the solution by method of joints for this simple truss. Now, the second method which we can use very effectively is the method of section, and mind you, this method is also very economical when you want to solve for forces only in few of the members, not in all the members. If it is to be done for all the members, then perhaps method of joints is easier, but when you want to calculate the or determine the forces only few of the members, not in all the members, then why to take all this trouble of solving for each and every joint? You can do it by method of section. Now, how does this solution proceed? In this solution, we will divide the whole truss into two sections. That is, we will think or imagine that the truss has been cut into by a section. This cut may be a plain cut or very crooked cut. So, depending upon your ingenuity and the type of members to be solved for, you can devise a suitable cut, and once the truss is cut into two parts, either you can use the left part for analysis or the right part, and then again by making use of the equations of equilibrium very judiciously, you can solve for the unknown member. So, this solution, this type of solution is very economical, very flexible, and sometimes in some of the problems you use method of sections plus method of joints, that is together, and this will make your solution very easy and simple. So, flexibility is very important characteristic of method of sections. Let me take up a problem to illustrate this method. Here is a truss. Again, I leave it to you to check that this truss, this plain truss is just rigid, okay, and obviously this is a simple truss. These are various joints and various forces over here. The supports are a simple support on this side and a roller support on this, and the loads are a 20 kilonewton at joint H, 10 kilonewton joint F, both are vertical, whereas there is a horizontal load also, sometimes wind loads on roof trusses. So, this is of the magnitude 10 kilonewton at point D. So, again the starting point is the truss has the whole truss has a free body. Well, here is again first you start with identifying your x axis and y axis. So, and then you say that the reactions at this simple support, both horizontal and vertical, are possible. So, Ay and Ax, you might be wondering why I have taken Ax towards left, whereas normally I have been taking the reaction, horizontal reaction towards right to make it positive. You can easily see that the load in the horizontal direction is 10 kilonewton towards right. So, without doing much effort, I can say that the horizontal reaction at A will be towards left, and not only that, its magnitude will be equal to 10 kilonewton, and at E there is only vertical reaction. So, these three equations, one sigma fx is equal to 0, sigma fy is equal to 0, sum of the vertical forces, again vertical reaction at A, vertical reaction at V, E, and two downward forces, and then moment about A is more convenient because there are two reactions passing through it. So, very easily you can find say that the horizontal reaction at x is 10 kilonewton, vertical reaction at A and E both are equal to 10 kilonewton. So, Ax is 10 kilonewtons, Ay and Ey are 10 kilonewtons. Now, let us see. We were asked to find out the forces in members CD, DG and HG, not in every member, only selected few, three of them. CD member, where does it lie? Here is CD. DG, here. So, looking at these two members, why not take a section over here? Okay. So, this will cut CD as well as DG. So, let us see. So, I will take a section over here and see that once the cut has been taken, I will consider the truss on the right side of the cut. So, this is the cut truss on the right. So, here is a just a minute. So, let us see, here we will be having if we solve for 10 plus A plus, there is an error here, this should be 15 kilonewtons, because AY plus EY is 30 and both will come out from here equal. So, it is 15 kilonewtons. So, this is 15 kilonewton vertical reaction. Okay. So, looking here, you will have, these are the given forces, 10 kilonewtons horizontal force, and at this point we have point F. So, this is point F. Okay. Now, first of all, we will solve for dg. Why? I will tell you. So, the forces FCD and the force FGF, which are produced due to this cut, this is this force FGF, they both pass through point E. Okay. So, if I take moments about point E, the moment of these two forces will be, and also this 15 kilonewton force, these three forces will have 0 moment over here. So, only the moment which will be produced by FDG and a known 10 kilonewton force over here. So, it means I can easily find out the unknown force FDG in just one step. That is by taking moments about point E, which should be equal to 0. Remember, in consideration of equilibrium, the choice of point O about which we take the moment is arbitrary. We can always select a suitable point about which we want to take the moment. So, whichever point can give me the solution most conveniently, I will choose that. So, I am choosing the point E to take moments, because all the unknown forces except one will have 0 moment over here. So, by taking this moments, let us see, there is a 10 kilonewton and this will produce a clockwise moment about E. So, clockwise are negative 10 into 3. So, minus 10 into 3 plus this will produce an anticlockwise 10 into 3 plus FDG. Now, this is angle 45, this is, so this total angle will be 90 degrees, it means DG is perpendicular to this. So, you can calculate this distance, because this is 3 meters, 6 meters. So, 6 into cosine of 45 degrees. So, you will get FDG is equal to 0. Okay. Then I will take the moment about point G. What will happen? This force FGF will have 0 moment, FDG will have 0 moment, only FCD will have a non-zero moment, and other two forces, or rather other three forces are known forces. So, it means in one step, in one go, I can find out FCD. This is exactly what we have done. That is, we have taken moment about point G. And so, it means in just 2 steps, that is taking moments about just 2 points E and G, I have solved for 2 of the 3 unknown members. So, it is very economical. Next, we want to determine the force in the HG member. Okay. So, here we will proceed from the left hand end and take a second free body, that is somewhere over here, HG. So, I will taking a free body like this. This is free body number 1, cut number 1, this is cut number 2. Okay. So, if I do this cut, so these are the members which are cut. So, again you can take moments about point B, right, because at point B the two of the unknown members are passing through, they will have 0 moment. Only the member in which we are interested in finding out the force, that will be there. So, and hence we can find out FHG is equal to 25 kilonewton tensile load. Okay. So, in this way all the 3 forces in 3 members have been determined in just 3 steps by taking 2 cuts. Now, we have considered so far the analysis of trusses, and one special feature of the trusses was that all the elements or members of a truss, they were supposed to take up only either a tensile load or a compressive load, that is the forces are along the length of the member, okay, or rather said it more accurately, about the line joining the 2 end joints of a member. So, there are other types of structural members called beams which can take up transverse loads, that is the loads which are either normal or at least oblique to the member itself. So, they are called beams. So, let us start with the analysis of beams. Beams are structural elements designed to carry transverse loads, okay, in contrast to truss members which were taking up only axial loads. These loads can be concentrated or distributed, they can be moving loads or stationary loads, that is dead loads, or loads due to some traffic, trains or vehicles, etc., or wind. So, not only loads, that is direct forces, but moments can also be supported by beams, whereas there was no such provision for the truss members, they were having only axial forces. Now, if there is a oblique load, as I have shown over here, an oblique load can be resolved into 2 components, a horizontal component and a vertical component, or a transverse component, axial component and a transverse component. So, the transverse component will produce tension or compression, whereas axial axial component will produce a tension or compression, transverse component will produce bending, okay, as we will see later on. So, in summary you can say beams are generally one dimensional members, that is one dimension length called length is much bigger than the other 2 dimensions. So, we will call them for simplification that these are one dimensional members subjected to either distributed loads or a concentrated load, transverse or oblique, or some couple having a moment which is acting on the beam. So, the role of beams is quite different from that of trusses, although both are structural members. Now, in the analysis of beams, again we will be restricting ourselves to statically determinate systems, that is the number of reactions from these end supports should be just equal to the number of unknowns involved, a number of equations of equilibrium. Okay. So, for example, here is a pin joint or a simple support which will have two reactions, a horizontal reaction and a vertical reaction, and the second is a roller support which will have only one reaction, only vertical reaction. So, three reactions and three equations of equilibrium in a plane. So, this structure is a statically determinate structure. Now, in the analysis of beams, we will introduce a very important concept, namely the concept of shear force and bending moment. Now, since the forces are applied forces are transverse, we have to see how they are to be withstood. That is, they will produce two types of reactions from the beam. One will be the shear force, a tangential force, and the other will be a moment called the bending moment. Now, to illustrate this, let me consider an internal free body. That is, this whole beam was arbitrarily cut. That is, you imagine that with the help of a knife we have, or a saw, we have cut the beam into two parts. One part on the left side and the other part on the right side. And since the beam is in equilibrium, each of the cut members or each of the sections will also be independently or individually in equilibrium. So, to maintain this equilibrium, let us say I consider the left hand section. These are the applied one force, second force, and perhaps another force over here, and this is the moment. Now, since the cut is passing through this, so as we have already done, there will be produced a tangential force acting through the section and a moment on that section. This is a moment, and equal and opposite moment on the right hand section and a tangential force. This was on the left hand section, if it is vertically up, on the right hand section it will be vertically down. So, by Newton's third law, actions and reactions being equal and opposite. So, this left hand section will be in equilibrium due to the applied loads, a shear force V and a moment M, and secondly, this right hand section is in equilibrium due to the reaction at this support, applied load V and M. Now, this force V or tangential force V is called shear force, and the moment M is called the bending moment. Now, a very important thing concept in the analysis of beams is the sign convention, and I must advise you that this has to be carefully done, otherwise errors are likely to happen. Suppose this is my rectangular Cartesian coordinates x and y, and of course z is out of the plane of the screen. Now, suppose I take an arbitrary section over here. It means I have cut the beam into two parts and two surfaces are produced. I will consider the outer normal on each of these surfaces. These are unit vectors. Outer normal means pointing away from the body of the section. That is, this is the section, so outer will be like this. In this case, the outer normal will be towards the left, here it is towards right. Now, if this outer normal is pointing in the positive x direction, then this surface is positive x. If this is pointing in the negative x, that is towards left, then this is a negative surface. So, a single cut produces one positive surface, one negative surface. And suppose there is a force over here, force F. If the force on a positive surface is in the positive x direction as shown over here, then the force is positive. If the force on the negative surface is also in the negative direction, that is negative x direction, then also such a force is a positive force. But if on a positive surface the force is in the negative x direction, or on a negative surface the force is in positive x direction, then the force is negative. So, this force is negative, this force is positive. So, remember, two positives or two negatives make a positive force, one positive, one negative will make a negative force. And similarly, considering the vertical forces, the previous were for the axial forces, now vertical forces. On a positive surface, a positive upward force in the positive y direction, or on a negative surface downward force, that will constitute a negative shear force. Similarly, on a negative positive surface, a negative downward force, or on a negative surface positive upward force, that will constitute a negative shear force. And same combination of signs will give me the positive bending moment or a negative bending moment. Again, on a positive surface, because here is the unit normal in the positive x, this is the unit normal. So, on a positive surface, an anti-clockwise moment, that is the positive moment, that will give me a positive bending moment. On a negative surface, a clockwise, that is negative moment, that will give me a, so two negatives or two positives will give you a positive bending moment, and similarly over here. So, this is a very systematic way of identifying positive shear force, negative shear force, positive bending moment, negative bending moment, positive axial force, negative axial force. So, we will continue with the analysis of beams, and I will certainly advise that you remember this simple but systematic way of identifying shear forces or bending moments which are positive, which are negative, because in literature different authors use different types of conventions, but this is the most easily understood convention. So, in the next lecture we will consider how to analyze various types of beams and their loadings and draw the bending moment and shear force diagram. Thank you very much.